Hey everybody, today we're going to be doing and or probabilities. If you don't know what that's all about, don't worry, we're going to start right now discussing it. Given that A and B are both outcomes of an experiment, we interpret the event A or B to be any outcome in which either A occurs or B occurs, or both. If A occurs, then this event A or B has occurred. If B occurs, then this event A or B has occurred. If both A and B occur, then this event has occurred. Now, what might be some scenarios in which this would be relevant? Let's look at a case where we draw a single card from a deck, okay? Consider this example. A single card is drawn from a deck of 52 cards. The event that the card drawn is an ace or a heart occurs when any of the following outcomes occur. So the event that we're looking for is that the one card that we draw is either an ace or a heart. And that event occurs when any of these things happen. If we draw an ace of clubs, yep, we got an ace. If we draw the ace of diamonds, yep, we got an ace. If we draw the ace of spades, yep, we got an ace. If we draw the two of hearts, yeah, we got a heart. We draw the three of hearts, yeah, we drew a heart, and so on and so forth. Or maybe the card that we draw is both an ace and a heart. In that case, the event occurs as well. So if we draw an ace, the event that we draw an ace or a heart occurs. If we draw a heart, the event that the card drawn is an ace or a heart occurs. If the card that we draw is both an ace and a heart, the event that the card we drew is an ace or a heart does occur. Now let's look at the probability for this thing. If A and B are outcomes of an experiment, then the probability that the event A or B occurs is given by the probability of A or B equals the probability that A occurs plus the probability that B occurs minus the probability that both A and B occur. Now, why would we have to subtract that? Well, first, let me change this from a definition to a theorem. The probability that A occurs or B occurs is the probability that A occurs plus the probability that B occurs minus the probability that both A and B occur. Why on earth would we have to subtract this? Well, I'll tell you what. Let's go back to the experiment where we're drawing a single card and we want to compute the probability that either we get an ace or we get a heart. Let's examine that. We draw a single card from a deck of cards, compute the probability that we get an ace or a heart, or both. These are the different ways that we can draw an ace. Ace of clubs, ace of diamonds, ace of hearts, ace of spades. 4 ways that we can draw an ace. The probability that we draw an ace, that's number of outcomes resulting in an ace over total number of outcomes four different outcomes result in an ace, and there are 52 possible outcomes, 52 cards in the deck. I tell you what, I'm going to leave it like this for the moment. Okay? Probability of a heart. That's going to be number of outcomes resulting in a heart over total number of possible outcomes number of outcomes that give us a heart. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 over 52. Probability that we get an ace or a heart is equal to number of outcomes resulting in an ace or a heart divided by total number of outcomes. Well, there are four outcomes that give us an ace. And there are 13 outcomes that give us a heart. But do you see a problem here? You might if you look very closely at the outcomes resulting in an ace and the outcomes resulting in a heart. Do you see a problem there? It's kind of subtle, but you might see it. I think this is a problem. These are one and the same outcome, but we're counting this as an outcome to get an ace. This is one of the four outcomes that give us an ace, which is where we get this 4 from. This is also one of the 13 outcomes that give us a heart. But we've counted this outcome twice. We've counted this outcome as an outcome here and an outcome there. We have to subtract the probability that we get an ace and a heart in the same card. Over total number of outcomes. Tell you what, let's take each term of the numerator and write it as a separate fraction over the denominator. So I'll take this 4, put it over, you know what? Total number of outcomes, 52, right? Okay. Now I'm going to take each of these terms in the numerator and write it as a separate fraction over the denominator. So we have 4 over 52 plus 13 over 52 minus 1 over 52. And look what we have here. 4 over 52. 4 over 52, that's the probability of an ace. And what about this 13 over 52? That's the probability that we get a heart. And this 1 over 52, what about that? This is the one card in the deck. This is the probability that we draw that one card in the deck that's both an ace and a heart. This is the one outcome, an ace and a heart, that we actually counted twice. And so to atone for that, we're going to have to subtract the probability that we get both, an ace and a heart. So 4 plus 13 is 17, minus 1 is 16 over 52, which is 4/13. Probability that we get an ace or a heart that's 4/13. In general, when we're computing the probability that one event or another event occurs, it's the sum of the probabilities that each of them occur minus the probability that both of them occur. The probability of A or B is the probability that A occurs plus the probability that B occurs minus the probability that they both occur. And why do we subtract this? If we don't subtract this, we're going to be counting the outcome that both A and B occur twice. So this is just to make sure that we don't count the outcome in which both A and B occur more than once. Here's another example, sort of like the first one. We're using cards again. I apologize, but to illustrate this kind of concept, a deck of cards is somewhat uniquely suited, which is why I'm using this particular kind of example over and over again. A single card is drawn from a deck of 52 cards. Compute the probability that the card is either a face card, that is Jack, Queen, or King, or the card is a diamond. So here's what we want. We want the probability of a face card, F, or diamond, D. And that's equal to the probability of getting a face card plus probability of getting a diamond minus the probability that we get both. Probability of getting a face card and a diamond. Probability of getting a face card. This is going to be number of outcomes resulting in a face card over total number of outcomes. Whoops. How many outcomes give us a face card? Jack, Queen, King of clubs, there's 3. Jack, Queen, King of diamonds, there's another 3. Jack, Queen, King of hearts, there's another 3. Jack, Queen, King of spades, there's another 3. So that's 3 plus 3 plus 3 plus 3. There are 12 ways that we can get a face card. Another way that we can look at it, we can get Jack of clubs, Jack of diamonds, Jack of hearts, Jack of spades, that's 4. We can get Queen of clubs, Queen of diamonds, Queen of hearts, Queen of spades, that's another 4. Or we can get King of clubs, King of diamonds, King of hearts, King of spades, that's another 4. So 4, 4, 4 gives us 12. Total number of outcomes, there are 52 cards in the deck. So these are the number of outcomes that give us, or rather, this is the probability that we get a face card. Now, what about the probability that we get a diamond? In each deck, there are 13 diamonds. There's 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King, Ace, 13. There are 13 diamonds in a deck. So the total number of outcomes resulting in a diamond over the total number of outcomes, period. That's going to be 13 out of 52. But what about those face cards that are both, or what about those cards that are both face cards and diamonds? That's the total number of outcomes where we have face card and diamond over a total number of outcomes, period. Total number of outcomes is 52. How many outcomes result in a face card and a diamond? Well, how many diamonds are face cards? There's the jack of diamonds, the queen of diamonds, the king of diamonds. That's 3. Okay, I guess we have all the numbers. Probability of F, 12 over 52. Probability of a diamond, 13 over 52. Minus the probability of a face card and a diamond, 3 over 52. 22 over 52, or 11 over 26. Probability of a face card or a diamond, 11 over 26. Here's a little bit of a twist. A single card is drawn from a deck of 52 cards. Compute the probability that the card is either a queen or a king. Sounds straightforward enough. Probability of a queen or a king. And that's going to be the probability that the card is a queen plus the probability that the card is a king minus the probability that it's both a queen and a king. And now maybe you're beginning to see why there's a little bit of a twist here. But let's work this out the same way that we've done the previous 2 exercises, because it will serve as a springboard for introducing another concept. Probability of getting a queen. We look at the number of outcomes resulting in a queen over the total number of outcomes how many outcomes result in a queen? Queen of clubs, queen of diamonds, queen of hearts, queen of spades. 4 outcomes result in a queen. Total number of outcomes, there are 52 cards in a deck, so that's the total number of outcomes. Let's do the same thing for a king. Probability of getting a king. It's going to be the total number of outcomes resulting in a king over the total number of outcomes, period. And how many outcomes result in a king? King of clubs, king of diamonds, king of hearts, king of spades. 4 outcomes give us a king. Okay, that's not 4. There we go. Total number of outcomes is 52. And here's where the new wrinkle comes in. Probability of a queen and a king. So that's the number of outcomes resulting in queen and king over the total number of outcomes, period. Total number of outcomes is 52. How many different cards in a deck are both a queen and a king? None. Okay. Probability of a queen, 452. Probability of a king, 4 over 52. Probability of both a queen and a king, 0 over 52. So this is really just 4 over 52 plus 4 over 52, which equals 8 over 52. And that's 2 over 13. Probability of a queen or a king is 2 over 13. Now, before we move on to the next exercise, let's take a look here at something that happened that hasn't happened in our previous exercises. We are looking at the probability of one event or another occurring. And these 2 events were such that they couldn't both happen. The probability of getting a queen and a king was 0. There were no outcomes in which both queen and king occurred. And look what the probability or the formula for the probability turned out to be. This thing, probability of a queen. This thing, probability of a king. Well, that's interesting. In this case, the probability of a queen or a king turned out to be just the probability of getting a queen plus the probability of getting a king. And we know why this result turned out to be different than the previous ones. What made this situation different, or this case different, is that they couldn't both occur. The probability of both queen and king occurring was 0. So first of all, let's talk about two events that can't both occur at the same time. There's a name for that. Here's the topic that our previous exercise or example leads us to quite nicely. The idea of two outcomes being mutually exclusive. Outcomes A and B are mutually exclusive if the occurrence of one precludes the possibility of the other from occurring, or if the occurrence of one makes the occurrence of the other an impossibility. From our previous example, queen and king are mutually exclusive outcomes. We draw a single card from a deck. If the card is a queen, then it can't also be a king. If the card is a king, then it can't also be a queen. Can we use this same example, drawing a single card from a deck? Think about it. We draw a single card from a deck. The outcome of club and diamond are mutually exclusive outcomes. If we draw a single card from a deck and that card is a club, then it can't be a diamond. If we draw a single card from the deck and that card is a diamond, then it can't be a club. The occurrence of one makes the other an impossibility. So drawing a single card from a deck, if that card is a club, then that card also being a diamond is an impossibility, and vice versa. They are mutually exclusive outcomes. One more example. A coin is tossed once. The outcome of getting heads and the outcome of getting tails are mutually exclusive. If we toss a coin and it turns out to be heads, then it's impossible for it also to be tails. If we toss a coin once and we get tails, it's impossible for that outcome to also be heads. The two are mutually exclusive. When one occurs, it makes the occurrence of the other one an impossibility. Recall, yep, I should put that word up here. Recall, if A and B are mutually exclusive outcomes of an experiment, then the probability that A and B both occur is 0. If they're mutually exclusive, then the occurrence of one makes the occurrence of the other an impossibility. So A and B can't both occur at the same time. It's an impossibility. The probability of A occurring and B occurring is 0. So again, if A and B are mutually exclusive outcomes, then the probability of A and B is 0. And here's a consequence. If A and B are mutually exclusive outcomes, if A and B are mutually exclusive outcomes of an experiment, then the probability of A or B occurring is just the probability that A occurs or the probability that B occurs. Now, why is that? Well, we know the probability that A or B occurs is equal to the probability that A occurs plus the probability that B occurs minus the probability that they both occur, A and B. But if A and B are mutually exclusive, then this thing equals 0. And so we just end up getting probability of A plus the probability of B. This is good. A single die is tossed one time. Compute the probability of getting either an even number or a 5. Okay. Probability of an even number plus probability of a 5. And let me ask you something. Can both of these things happen at the same time? If we toss a die once, can we get both an even number and a 5? Nope. These are mutually exclusive. So we don't have to subtract the probability of getting an even number and a 5. So we're going to get number of outcomes. Whoops. Let me do it the way I've been doing it before. Probability of even number, number of outcomes, resulting in an even number over total number of outcomes. And how many ways can we get an even number if we roll a die? 2, 4, 6. Those are the only possibilities. So 3 ways of getting an even number. There are 6 possible outcomes. Probability of getting a 5, number of outcomes resulting in a 5 over total number of outcomes. There's only one way we can get a 5. 6 possible outcomes. Probability of E is 3/6. Probability of 5 is 1/6. Now, could we have done this another way and not really given much thought ahead of time as to whether these things were mutually exclusive? We saw right off the bat that getting an even number and getting a 5 were mutually exclusive. Suppose it didn't occur to us right when we started. Doink, oh, they're mutually exclusive. Suppose that didn't happen and we didn't realize till later that these two outcomes were mutually exclusive. What would have happened? Let's take a look. We'll do this again. And here we don't know, or we haven't figured out two outcomes are mutually exclusive. So we're going to subtract the probability of getting an even number and a 5. Probability of an even number of outcomes that yield an even number over total number of outcomes. And there are 3 ways we can get an even number, 2, 4, or 6, over 6 total outcomes. Probability of getting a 5, number of outcomes resulting in a 5 over total number of outcomes. There's only one way we can get a 5 with a single die, and total number of outcomes is 6. And then we compute the probability of getting an even number and a 5, and that's total number of outcomes, E and 5, over total number of outcomes, period. Total number of outcomes is 6, and how many ways can we get an even number and a 5? And we go 2, 4, 6, and we go, oh, we can't get both an even number and a 5, so this is 0 outcomes resulting in both an E and a 5. Well, what happens if we put all of these things into this formula? Probability of getting an even is 3 over 6. Probability of getting a 5 is 1 over 6, minus the probability that they both happen, which is 0 over 6. But we get the same thing. If we use this formula, this probability is just going to turn out to be 0, and we're going to get the same answer that we got before. Okay, next up, we're going to do something completely different. And this applies exclusively to multi-stage experiments. Two-stage experiments and probabilities. Given a two-stage experiment in which A is an outcome of the first stage and B is an outcome of the second stage, the probability that A and B occur is the product of the probabilities that A occurs in the first stage times the probability that B occurs in the second stage. And our authors tell us this experiment is performed in such a way that it is understood that A occurs before B. We can say that it's the context of the experiment that A occurs before B occurs. Here's an experiment. A coin is tossed, and then a single die is tossed. Compute the probability that the coin is heads and the die shows a 5. Okay, it's a two-stage experiment. A coin is tossed, that's stage 1. A single die is tossed, that's stage 2. And what we want the probability that the coin is heads and the die is a 5. This is a two-stage experiment. This is an outcome of the first stage. This is an outcome of the second stage. And according to our formula, we're going to get the probability of heads occurring in the first stage and the probability of getting a 5 in the second stage. Probability of heads, number of outcomes resulting in heads over total number of outcomes. There's one way we can get a head, and there are only 2 outcomes. Probability of getting a 5, number of outcomes yielding a 5 over total number of outcomes with a single die. There's only one way that we can get a 5, but there are 6 possible outcomes. That was easy. We toss a coin, we roll a single die, the probability of getting heads in a 5, 1/12. Let's do another one. Another dice problem. We're taking a single die and we're tossing it twice. Compute the probability that the first toss results in a 6 and the second toss results in a value greater than 4. The first toss, that's stage 1 of the experiment. Second toss, that's stage 2 of the experiment. This is a two-stage experiment. And the first toss, we want to result in a 6. So that's A. The second toss, of value greater than 4, that's B. Let's see, probability of A, number of ways or number of outcomes resulting in A over total number of outcomes. We toss a single die and we get a 6. There's only one way that that can happen. Whoops. I said there's only one way that can happen, okay? And there are 6 total outcomes. B, we get a value greater than 4. How many faces on a die have a value greater than 4? There's one that has a 5 and there's one that has a 6. There's 2 ways, 2 outcomes that produce a value greater than 4. So the number of outcomes that produce B, something greater than 4, that's 2. Total number of outcomes is 6. The probability of A in the first stage and B in the second stage is probability of A times probability of B. And that's going to give us 1/6 times 2/6, which equals 2/36, or 1/18. Probability of A and B, 1/18. A card is drawn from a deck, observed, and returned to the deck. The deck is well shuffled. A card is drawn from a deck, observed, and returned to the deck. So 2 cards are drawn here. And from the last video, we might remember the terminology here. The cards are drawn with replacement. We put the first card back in the deck so that it might be drawn again. The cards are drawn with replacement. And the fact that the deck is well shuffled after the first card is returned means that every card in the deck is equally likely to be chosen. So the first card that we drew is just as likely to be chosen as the second card as it was the first card. Another way of saying this, we pick a card from a deck, we put it back, and we shuffle the deck. When we pick the second card, no card in the deck is more likely to be chosen than any other card in the deck. That's what well shuffling means. We want to compute the probability that both cards are aces. We want the probability of an ace on the first draw and an ace on the second draw. And the probability of an ace on the first draw, that's the number of outcomes resulting in an ace over total number of outcomes. There are 4 aces in the deck and 52 cards that can be chosen. Now, what about the second draw? Probability of an ace on the second draw, number of outcomes resulting in an ace over total number of outcomes. Well, really nothing's changed. There are still 4 aces in the deck, and they're all equally likely to be chosen. And there are 52 cards in the deck total. The probability of A being drawn on the first card in the first stage and an ace being drawn in the second stage, that's the probability of an ace in the first stage times the probability of an ace in the second stage, and that's 4 over 52 times 4 over 52. Good grief. Let's reduce these fractions. 1/13 times 1/13, that's 169. Probability of getting an ace on the first draw and getting an ace on the second draw, 169. And let me just encapsulate that result in a red box so that we are absolutely sure what the answer is. No misgivings here. The probability of getting an ace on the first draw, getting an ace on the second draw, 1 out of 169. Not very good. Now let's do this again, but do a little twist. A similar exercise, a card is drawn from a deck, observed, but it's not returned to the deck. And then a second card is drawn from the deck, observed, it's not returned to the deck. Compute the probability that both cards are aces. And from our discussion in the previous lecture, we know that these cards are drawn without replacement. So we compute the probability that the first card is an ace and the second card is an ace. And in these multi-stage experiments, we always assume that this thing happens and then afterward that thing happens. So the probability that we get an ace on the first card, number of outcomes resulting in an ace over total number of outcomes. Well, there were 4 aces in the deck and 52 cards in the deck. Nothing's changed. Everything's exactly like it was in the previous example so far. Now, let's compute the probability that the second card is an ace. Number of outcomes resulting in an ace over total number of outcomes. Here's where it gets tricky. We selected the first card, but we didn't put it back in the deck. So when we're selecting the second card, how many aces are left in the deck? If this first card was an ace and we never put it back in the deck, how many aces are left in the deck when we draw the second card? 3, that's right. Only 3 aces left, so that's the number of outcomes resulting in an ace. And something else is different too. If we selected this first card, which was an ace, and we never put it back in the deck after we selected that first card, how many cards are left in the deck when we select the next card? There's only 51 cards left in the deck. Okay. So we have the probability of an ace on the first stage and getting an ace in the second stage. That's the probability of an ace in the first stage times the probability of getting an ace in the second stage, and they're going to be different, The first stage, the probability is 4 over 52. The second stage, the probability is 3 over 51. And good grief, I'm going to cancel here. 4 over 52 is 1 over 13. And 3 over 51, I think, is 1 over 17. Anybody know what 13 times 17 is? Holy moly. Okay, 21, 1. Okay. 1 over, is that right? Let's see. 1, 6. No. 21, 3 times 1 is 3, 5, 7 times 7, 1. I can't add anymore, forgive me. 1 over 221, okay. Probability of getting an ace on the first draw and an ace on the second draw. If the cards are selected without replacement, 1 over 221. Now let's see. I think when we did it with replacement, it was 1 over 169, right? So, wow, there's a big difference. If the cards are drawn without replacement, it's going to be a lot harder to get an ace on the first draw and on the second draw. And let me mention one other thing in case you're worried about this. I wrote the experiments this way just so that there wouldn't be any kind of distraction. But if this is just a two-stage experiment, and I draw the second card from the deck and don't return it, does it really make a difference? It doesn't. I didn't return the first card to the deck, and that made a difference because we were going to draw a second card. I didn't return the second card to the deck, and that's really not going to make a difference because I'm not going to draw another card after the second card. So really, the only important thing here was that the first card was drawn from the deck and not returned. What we did with the second card after we drew it from the deck made absolutely no difference at all. The fact that the first card was not returned was important because we were going to draw another card after the first card. But whether we returned the second card or not made no difference because we weren't going to draw another